Hello and welcome to this further maths video looking at matrices for 3D transformations and also inverse transformations. So just like with a transformation in 2 dimensions, we can transform things in 3 dimensions. It's a little bit harder to visualize, but we can still use matrices to do a lot of the work for us. So you're not given any of the 3D transformations in the formula book. So you need to learn these really. Certainly the rotation. So what you are given in the formula book, which helps, is the rotation of theta degrees anti-clockwise about the origin for 2 dimensions. So that looks like that. So if you want to rotate about the x-axis, so if you think of the x-axis being here, and we're going to rotate, that's going to be our axis of rotation, and we're going to rotate an angle theta, then that would be represented by this matrix. So because we're going about the x-axis, we get 1, 0, 0 in this column, and then we get this same matrix for a 2D rotation nesting inside it. About the y-axis, if we rotate about the y-axis, then the same sort of thing happens. The y-axis stays where it is. So if you think of this is the point 0, 1, 0. So 0, 1, 0 stays where it is. If you cross out that row and column, we have minus this. The signs are, the negative on the sign is the other way around. Then for the z-axis, again, the z-axis, the point 0, 0, 1 stays where it is, and this nests inside it. So really, you need to learn these. And in particular, you need to learn what happens with this one here. Right, enlargements and reflections. Enlargements, fairly straightforward. If you think what happens to 1, 0, 0, it's going to be mapped onto lambda 0, 0. So each of the axes will be stretched by a scale factor of lambda. Reflections, you need to be able to work these out. So let's just think what happens. If we reflect in the plane x equals z, x equals 0. So if you think about points in 3 dimensions, and we're looking at the points where x equals 0, that's all the points in the YZ plane. It's all of this sort of vertical plane slicing down, because try plotting some points where the x is 0 and you would have 0, 1, 1. So that would be that point there in this wall, if you like. So then let's think where our unit vectors end up. So 1, 0, 0 is here. Under a reflection in this plane, in the YZ plane, which is the plane called x equals 0, that will map to minus 1, 0, 0. This point here, 0, 1, 0, stays where it is in that reflection because it's in the reflecting plane. So that's 0, 1, 0. And this point here, 0, 0, 1, also stays where it is. So that gives us this matrix here, which is the reflection in x equals 0. And we can work these ones out as well. So I think you can work these ones out. These ones I would learn. So let's have a look at a couple of questions on this. So it says find a matrix representing a reflection in the plane z equals 0. So just make sure you know which plane that is. So we've got our axes here, and this is x, y, and z. Get used to trying to draw in 3 dimensions, you will get better at it. So if I want the points where z equals 0, this is the plane, the horizontal plane that's the floor, if you like. So where do our unit vectors end up? Now I'm going to try and draw them all on top of here. So where does this point here end up? 1, 0, 0, that stays where it is. Where does 0, 1, 0 end up? That stays where it is. But where does this point here end up? 0, 0, 1. That will be reflected down to here. So that's going to end up at 0, 0, minus 1. And that is my matrix for that transformation. Question 2 here says, what's a rotation of theta degrees about the x-axis? So if we're rotating about the x-axis, think about rotating. So I draw my axes again, so x, y, and, oops, there's a mistake there, y and z. So if we're rotating about the x-axis, anything on that axis will stay where it is. So we've got that 1, 0, 0 sitting like that. And we then fill in the zeros, and then we put in here, because it's the x-axis, it's just like rotation in 2 dimensions. So we've got cos theta, sine theta, minus sine theta, and cos theta. And that gives us our rotation. Right, let's have a look now at inverse transformations and how we can use the inverse of a matrix to help us work through this. So if we've got a transformation, then the inverse of the matrix that represents that undoes the transformation. So some things are self-inverse. So reflections are self-inverse, because if you reflect in a line and then reflect in another line, then that is going to get you back to where you started being. Let's just get the visualizer to focus a bit better. A rotation of 180 degrees would also be self-inverse, because if you do a 180 degree rotation and then another 180 degree rotation, you'll get back to where you started. So let's see how this works out. We've got a matrix A representing a transformation T. So it says that T maps the point with coordinates x, y onto a point P dash with coordinates 6, 10. Find the coordinates of P. Now, in this question, I'm going to do it 2 ways. You could do it using simultaneous equations, and I think in 2 dimensions that's probably the easiest way to do it. We've got the matrix here, we're multiplying the point P, and we end up with 6, 10. So if we write out the simultaneous equations, we get 2x plus 4y equals 6, and we get minus 2x minus 5y equals 10. And if I solve these 2 equations, I get x is 35 and y is minus 16. And you can check that yourselves, or you can use your calculator to do it, but that's fairly straightforward. So the original point was, it says find the coordinates. I would make it very clear that P is the point 35 minus 16. So when we transform it using this matrix A, the transformation T, it maps onto 6, 10. If I wanted to do it using an inverse matrix, first thing I need to do is find the inverse of A. Now the inverse of A, we need to work that out. So the first thing we're going to do is 1 over det A. Now what's det A going to be? It's going to be minus 10, take away minus 8. So that's going to be minus 2. So the determinant of that is going to be, let's just check it's minus 2, minus 10, minus 2. And then we are going to work out the other points here. So we switch these ones over. So we've got minus 5, 2, and we've changed the signs here, minus 4 and plus 2. And then it's going to make sense to bring that minus 2 into this. So that becomes 2.5, 2, minus 1, minus 1. Just double check that we've got that right. Yeah, so that's the inverse matrix. So what we know, if you think about this here, is that if I pre-multiply this equation, if you like, by the inverse, then I'm going to work out what that will give me, what xy is equal to. So let's see how that works. If I write down the inverse, 2.52 minus 1 minus 1, multiplied by the original matrix, 2, 4, minus 2, minus 5, multiplied by xy, so this is the original question that I've been looking at, then that's going to be equal to, and I've got to do the same thing to both sides of my equation, so 2.52 minus 1 multiplied by 610. So I'm doing the same thing to both sides of this equation. I'm multiplying by A inverse. The reason I'm doing that is that this is going to give me the matrix 1, 0, 0, 1, because that's the definition of inverse. So this is going to give me that this is just going to be xy on this side is equal to, now when I actually do this multiplication here, what do I get? 15 plus 20 is 35, minus 6 minus 10 is minus 16. So that gives me the point P is going to be 35 minus 16. Now that feels quite long, but of course in 3 dimensions that is going to be a quicker approach to take, or if you're given some awkward algebra that you've got to work out. Right, part B of this question. You're told that B represents a transformation U, and what we've got is that the transformation T, so that's A, the matrix A, followed by U, is equivalent to a reflection in the line y equals x. So which one comes first? So the transformation T, so that is the matrix A, followed by, so remember the order matters here, that if we do it in that order, that's a reflection in the line y equals x. That's what the question's told us. And a reflection in the line y equals x is given by that matrix there, 0, 1, 1, 0. Sorry, that's a 1 there. Okay. Now, we are asked to find out what this matrix B is here. So we're going to use some matrix algebra for this. I've got BA is equal to this matrix here, multiplied by it. So what I'm going to do is I'm going to post multiply. So I'm going to put A inverse at the end is going to be equal to 0, 1, 1, 0, post multiplied by the inverse matrix 2.52 minus 1 minus 1. And when I do that, I get that B is equal to minus 1, 2.52. So these combination ones, where you've got to use the inverse, you've got to think quite carefully about how you work that out. But if you write out the matrices in the order that corresponds to the transformations used, and write out the matrix you know that that's equal to, then think how you can use your inverse matrix to get to the one you're trying to find that's on its own. And that gives me the solution there.